All right, I think I'm ready to get started. Welcome back, everybody. Today is the due date for your test revisions. I know some people at least have been working on them because I've been talking to some people about it. Please let me know if you have any questions. I would be happy to help you out. I won't tell you the answers, but I'll give you some hints, and I'll try and help out as much as I can. Don't wait till tonight to ask me questions because I might not get back to you if you wait too long. All right. Does anybody have any questions about the test revisions? Send them to GradeScope. Only redo the ones that you want me to regrade. If you turn in new work, if you skip some, I will just keep your old grade for those questions. All right, please let me know if you have questions. I'm happy to go over it. But for now, we are going to continue talking about compact sets, and in particular, the Heine-Borel Theorem. The Heine-Borel Theorem. This is the last thing that we're going to say about compact sets. This is a theorem which tells you what sets are compact. So in addition to the definition of compactness, there's two other important characterizations of compactness. So the theorem, anyway, it tells you that all of these things are equivalent. So the theorem says the following are equivalent. I wrote this at the end last time, but I might as well write it again. The Heine-Borel Theorem. It's a big name theorem. So number one, some set K, subset of R, is compact. All right? And remember, the definition of compact means any sequence in K has a convergent subsequence with its limit in K, right? Any sequence, that's the definition of compact. Any sequence in K has a convergent subsequence whose limit is also in the set that you're talking about, K. All right, that's the first thing. So that is equivalent to, number two is that K is closed and bounded. All right. The statement of the theorem says the following are equivalent. So compact, the definition involving limits, is equivalent to saying that K is closed and bounded. And we already proved that last time, or maybe even the time before. The part that I want to talk about this time is statement number three, and this is the one having to do with open covers, and it says any open cover of K has a finite subcover. All right. Actually, often in other books, and actually in most, pretty much any topology book that you would look at, this would be taken as the definition of compactness. So if you ask a topologist what does compact mean, they are likely to say this: any open cover has a finite subcover. That is equivalent to the statement about sequences, and also equivalent to the statement about closed and bounded. This is the Heine-Borel theorem, one of the big, theorems in real analysis. All right, now I want to talk about why this is true, but like I said, we've already shown quite a bit of this. So 1 and 2 are equivalent. This we showed last time, or actually I believe it was the time before, but I'll just say we showed already. All right, what I want to talk about today is 2 and 3. So today, this won't be the only thing we talk about, but I want to talk about 2 if and only if 3. All right. Closed and bounded is the same as saying any open cover has a finite subcover. Why are those two related? Actually, you don't even need to use the first one at this point. We're just talking about closed and bounded, and open cover has a finite subcover. Just to refresh your memory about what an open cover is, remember an open cover means you have your set here, K. I draw it as if it looks like an interval, but a compact set doesn't have to look like an interval. And then an open cover is some bunch of open sets which cover up the entire set of K. And closed and bounded, what we want to demonstrate is any closed and bounded set has this property that an open cover has a finite subcover. So this is if and only if. I want to do each direction of the argument. So first, let's talk about 3 implies 2. All right. So I'll say the proof. We're going to do this one in some amount of detail. We're also going to do 2 implies 3, but only in less detail. So 3 implies 2. So 3 says any. We're going to assume any open cover has a finite subcover, and then we have to prove that it's closed and bounded. So I'll say assume any open cover of K has a finite subcover. And then I want to show K is closed and bounded. All right. Actually, half of this is quite easy because we already talked about half of this. So we have to show closed and bounded. Let's do bounded first. Bounded is the easy part. We've already seen that if K is unbounded, some open covers have no finite subcover. We saw this last time. That's because if K is unbounded, then you can make an open cover like this that goes all the way out this way, right? And that open cover requires infinitely many of those steps. You can't just take only finitely many and still cover all of K because K is bounded. If you take only finitely many, you're not going to stretch all the way out to the end. I mean, there is no end. You're not going to be able to stretch all the way out. So if K is unbounded, then some open covers have no finite subcover. The contrapositive of that, though, if you just say this the other way around, what that means is, I'll just say equivalently, if any open cover has a finite subcover, I'm saying the contrapositive, that is the, P implies Q, the contrapositive is not Q implies not P, and they are equivalent. If any open cover has a finite subcover, then K is bounded, right? I took this and made the contrapositive of it. We said if K is unbounded, then some cover has no finite subcover. The contrapositive is if every open cover has a finite subcover, then K is bounded. And that's what we wanted to show in this step. Right? We assume that K has any open cover of K has a finite subcover. And we wanted to show that K is closed and bounded. So bounded is for free. This is something we already talked about last time. What about closed? That's the more difficult, I suppose, although it's not super difficult. What about closed? So this time I'm going to assume that, or no, I want to show that K is closed. Remember, closed means it includes all of its limit points. Every limit point of K is an element of K. So to show that a set is closed, I'm going to say something like let X in K, not in K, sorry, I have to show that it's in K. Let X be a limit point of K. And then I want to show that X is in K, right? If X is a limit point, then X is in K. This will suffice to show that K is closed, because that would mean that K includes every limit point of K. That's what it means to be closed, all right? So I want to show that X is in K. How about this for the sake, I'm going to do this by contradiction. Assume that X is not in K. And then the situation I have, I'll try and draw a picture of it. I have my set K like this maybe, and let's say it has a limit point which is not in the set. That means that X would have to lie sort of on the edge like that, but not part of K. So this over here is K. X is a limit point, but it's not in the set. So you should imagine something like an open interval which is missing one of its endpoints. But anyway, since x is a limit point, that means we can find a sequence of points which go, sort of march right up to x. So since x is a limit point, there exists a sequence. You know, on the picture, a sequence of points sort of like this. These points are in K and they approach the X, right? That's what it means to be a limit point, or that was a theorem at least we had. X is a limit point of K means you can find a sequence in K of points which approach X. So since X is a limit point, there exists a sequence. Maybe I'll call it AN in K. And the limit of those things are is X. AN approaches X. All right. Now we have to use this open cover business. That's what our assumption or our hypothesis in this part of the theorem. If every open cover has a finite subcover, then the set must be closed. How do we make an open cover out of this? Actually, I'm going to sort of zoom in on this picture. What we have here is, let's say X is over here, that's the limit point, and we have these points of my sequence. They converge to X, right? Since they are a sequence, I can make a weird open cover like this. I'm going to, around every point here, I'm just going to make a cover. So around this point, I'm going to put, this is similar to an example we saw last time. Around this point, I'm going to go up that far and only over here. So these intervals, not there. What I'm doing is I'm making an interval every time the right-hand endpoint goes over to X, and then it just goes over to the left however far it has to be, just so that it's sort of a symmetrical interval around each of these points. This way. All right. I am making neighborhoods around each point. The neighborhoods that you use, they shrink down the closer you get to X. These neighborhoods are always chosen to cover the red points, but they never actually cover X, right? Right? Okay, so this is an open cover. So if I were to write this out in detail, I would say let ON be the, really what I'm doing here is I'm taking the neighborhood. Sorry, I've done this slightly wrong. Would you forgive me if I took, actually I don't want that whole blue set, I want only half of its radius. Oh, this is a disaster. I'm going to erase half. I want only half of that every time. Sorry about that. So each of these neighborhoods goes from the point that I'm talking about and then halfway across to X. So I'm going to redraw these ones. Sorry about this. I wasn't looking carefully enough on my paper. Only half the way to X. And then it doesn't really matter how far it stretches to the left, but we might as well just make it symmetrical. So each one goes half of the way to X. This one goes half of this way, and so on. This one goes half of the way to X. All right, etc. All right. So in some fancy language here, ON is the neighborhood around AN, whose radius is AN minus X over 2. Sorry, I have it in absolute value. The radius of each of these sets is half the distance from that point to X. All right. I hope I got this right. I think I got this right. The radius of each of these little open sets is half the distance from that point over to X. All right. This is an open cover of the sequence. Would you believe that? I think it is. This is an open cover of these points. And if I take this for every point in K, so for any X in K, it's only important really that you do this around the sequence points, but really I'm going to do this around every point. I shouldn't say X again. X is the name of the limit point. Let me call it, can I call it A? For any A in my compact set, I'm going to let OA be this same thing that I just said. So don't just put it around those sequence points, put it around every point of A. And this is an open cover of K. All right. But if you look at the picture, I think you will agree with me. There's no way you can make this you cannot do this as a finite subcover because X is not part of K, so X does not have its own blue neighborhood around it. If you want to cover all the sequence points, you need to use infinitely many of these blue sets because if you stop at any one of them, you're going to miss some of the red points, right? Because that's why it's important that radius doesn't go all the way to X, it goes only halfway. If you only take some of the blue sets, you will not be able to capture all of the red points. So this is an open cover of K, but it has no finite subcover. Because if I choose only finitely many of those blue sets, I'm going to miss some of the red points. All right. And this is a contradiction with our assumption that any open cover of K has a finite subcover. So this contradicts our assumption about open covers. Remember, this was a proof by contradiction. Assumption that any open cover has a finite subcover. All right, that's how we do it. So this demonstrates that, remember what we just showed was 2 implies 3. So let me just remind us. So we showed that closed and bounded, sorry, no, it was 3 implies 2, that this condition, every open cover has a finite subcover. Implies closed and bounded. All right. Open cover is what that says. Come on now. All right. I do want to talk about the other way around too. If it's closed and bounded, then it means that every open cover has a finite subcover. Although this one I said I wasn't, I don't want to do a detailed proof of this. Really, I'm just going to sort of draw a picture and give you the idea of why every, if it's closed and bounded, then it must be the case that every open cover has a finite subcover. Check it out. Closed and bounded. So I want to now do the other way around, which is 2 implies 3, right? Actually, this is the hardest step of the proof, and this part of it is the part which was done by Heine and Borel. This is two different people's names on this. This is the hard part, and the part which it is what was deserving of the name, the Heine-Borel theorem. So for this one, we're going to go the other way around. So it says let K be closed and bounded. And then also take any open subcover, or any open cover. So I'm going to say let O lambda be an open cover. And then we want to show that there is a finite subcover. Right. We assume it's closed and bounded, and then we're going to show this open cover. Every open cover has a finite subcover. All right. So the first thing, like I said, I'm not going to do all the details of this. The first thing towards the end of not doing all the details, I'm just going to draw some pictures, and let's just imagine that K is a closed interval. So the real theorem is not just for closed intervals, but I'm just going to say let's consider if K is a closed interval. It's not so hard to redo this proof with any compact set. Any closed and bounded set. but it's easier if it's a closed interval because I'm going to use the nested intervals property. If you want to do this the real way, you have to use more like the nested compact sets property, which is a little more complicated. Anyway, let's just consider if K is a closed interval, the picture looks like this, right? Let's call this K. Now, I already gave away the main tool here is going to be the nested interval property. So I'm going to call this I1, and I'm going to describe how to create a bunch of smaller intervals towards the end of using the nested intervals property. Let's say this is K, and we also have some open cover of K, which I'm going to just draw like this, like I usually do. This consists of a whole bunch of open sets which cover up all of K. And this open cover, we don't know if it's finite or not. That's our whole goal, is to show that there is a finite subcover. So we might as well, when we're drawing the picture, act like there's not, act like it's not finite, right? What it means if it's not finite is like somewhere along here, there's actually infinitely many of them. And that means, in fact, that these infinitely many, maybe it's only finite, like on the right side. Maybe there are only finitely many ones here, but over here somewhere, there's a place where, for some reason, there's infinitely many of them. All right. Here's how I do the nested intervals. I'm going to repeatedly cut this interval in half. This is like the Bolzano-Weierstrass theorem. We're going to cut the interval in half over and over again, and every time I cut it in half to capture like the infinite side. So this is I2. And I'm going to, here, I'll write down here exactly what I'm doing here. We bisect the interval each time, cut it in half, and choose the half which uses infinitely many sets in the open cover. All right. Now it may be there may be infinitely many sets on both sides, and so then you choose either one at random. It doesn't matter. All right. Now in this particular example, it looks like those open cover sets, they kind of cluster up on the left, and then I'm going to cut this one in half. It looks like the place where you really need infinitely many is somewhere like in there, right? So I'm going to cut it in half on that side, and then continue. Maybe this side, etc. So this is I3, I4, all right? Now, we have to demonstrate that somehow you can do this using only finitely many sets, like only finitely many of these original sets are necessary to cover K. So the argument will go something like this. For the sake of a contradiction, assume we need infinitely many of these sets. All right. But then we do this interval bisection. Each stage, we choose the half which requires infinitely many sets in the open cover. But by the nested interval property, when we do this intersection, we end up with one point in all of these intervals, right? It goes down eventually, shrinks down to a single point, which I call x. Why does it have to be a single point? Well, the nested interval property says the intersection of all of these is not empty, but because I'm cutting in half every time, it can't become some other interval. It will actually shrink down all the way to a single point. So we end up with one point x. But because of the construction of how we chose the intervals every time we're choosing the interval to be the side which requires infinitely many sets. So if we choose this correctly, then this single point x requires infinitely many sets to cover. And this is a contradiction because a single point does not require infinitely many sets to cover. It only requires one set, right? That point, there's no way that a single point can require an infinite cover it can just be covered by a single set. And so then this single point X requires infinitely many sets to cover, and this is a contradiction. All right. I don't know if this is really possible to hold the whole idea in your head, but the idea is a closed and bounded set. Even if you cover with infinitely many things, you only need finitely many of them to cover the whole set. If you think you need all infinitely many, you can keep on cutting the set in half, and eventually you'll get down to something so small that it only requires finitely many things. In this case, we made it all the way down to a single point, which obviously doesn't require infinitely many sets to cover it. All right. This is the Heine-Borel Theorem. I had a professor in grad school actually who claims, I don't have any verification of this story, he claims that he went once to like a political protest in Washington D.C. and he was carrying a big sign. He was with his friends carrying a big sign that says "Mathematicians for Peace." I think this was like during the Vietnam War or something. And somebody walked up to him and said, "Oh, hey, are you guys really mathematicians?" And he said, "Yeah." And he said, "Oh yeah? Well, what's the Heine-Borel theorem?" And he said, "Well, it says that compact sets are closed and bounded and they have the open subcover property." And they said, "All right, I guess you guys are mathematicians." So the Heine-Borel theorem, he always said, this is useful in the real world because of that. It is a way of describing compact sets. Compact sets means they are closed and bounded, and it also means that any open cover has a finite subcover. Are there any questions about that? I know this is a little heavy duty, especially to do first thing after the weekend. And I'm not sure we are fully remembering what we talked about last week. But that's the Heine-Borel theorem. You'll have a chance to do some homework problems about it. All right. I thought maybe we'd do one kind of application, which is, I don't know if you remember, but a couple times ago we did the first few parts of a comprehensive exam problem. I just want to revisit and do the last part of that problem. So this is comprehensive exam from 2019, and we were discussing number 24. I want to do part F. We did A, B, C, D. Part E says, state the Heine-Borel theorem. So you just write, the following are equivalent. K is compact, K is closed and bounded, and any open cover of K has a finite subcover. That's the statement of the Heine-Borel theorem. The part F, this is very easy, I think, if you have your wits about you. It says, prove using the Heine-Borel theorem, I'll write HBT, that Z is not compact in R. All right. Prove that the integers is not compact. So the Heine-Borel theorem, remember, says compact is equivalent to closed and bounded, and also equivalent to every open cover has a finite subcover. So can you demonstrate that Z is not compact? Anyone want to shout out? How do you know Z is not compact according to the Heine-Borel? You should say something perhaps about closed and bounded, or something about open covers. Even if you didn't follow the proofs that I just did, you can still answer this question.
Is it because Z isn't bounded or closed?
Yeah, because Z isn't bounded. Actually, Z is closed. Z has no limit points, and so vacuously Z does contain all of its limit points. But compact is equivalent to closed and bounded, right? And also equivalent to the open cover thing. But for the purposes of this question, that's not necessary. Open covers have finite subcover. But that part doesn't matter. Because Z is not bounded. Actually, it is closed, but it doesn't matter. Z is not bounded, so it's not closed and bounded, and so it's not compact. Right? The Heine-Borel theorem, it gives you a fairly easy way to judge if something is compact or not. Easier than things about sequences. You know, the definition of compact is about a sequence has a convergent subsequence which is in the set. Sometimes harder to manage. All right, so this is all you should have said for the answer to that comprehensive exam problem. Provided you were able to remember the Heine-Borel theorem, it's an easy one. All right, any questions about that? This is actually the end of what I want to say about compact sets, and what we're going to talk about next, in my opinion, is considerably easier. At least the idea of it is a lot more intuitive. So if you zoned out for the past 15 minutes or so, please zone back in. I can't tell on the Zoom if you're zoned or not, but what we're about to talk about, I think, is considerably more intuitive. That is, an ordinary person thinking about sets in the real numbers is probably unlikely to come up with the idea of compact by themselves, just because it's kind of a complicated idea. The next thing we're going to talk about is an idea that I think everybody would think of like on their own, and it's called connected sets. Connected sets. A connected set is, well, it's such an intuitive idea that it's hard to say, hard to describe without using the word connected. It means like the whole set is like in one piece. It's not in two separate pieces. It's connected. So this is an example of, say, easy to imagine what this means, but it turns out to be a little bit hard to define. Not super hard, but you have to think a bit to come up with a good definition of this concept. But the idea of the concept is very natural, I think. Connected sets. So, for example, if I have a set that looks like this, this is connected because it's all like in one chunk, versus this is not connected because it's in 2 bits. All right, so this is the idea of connected versus not connected. Now, those pictures are very simple. Can I say some examples, maybe a little slightly more interesting? I don't know. How about all of R as a set? All of R is connected because if you were to draw a picture of it, it's just all like one thing all together. It doesn't have 2 pieces to it or something like that. So R is connected. Something like any interval is also connected. So something like the interval a to b, right? That is connected. Connected. I can spell right. Whether it's closed or open, it's connected, right? This is also connected because it still is in all like one piece, right? The open interval a to b is also connected, or even open on one side, closed on another side, right? This is connected. Even if it were infinite on one side, right? This is connected. I didn't tell the definition of connected yet because it's a little weird, but you should imagine if you just look at a picture of these, it looks like it's all in one piece. It's not split out into 2 pieces. All right. What about n? N is an example of something which is not connected because, well, this one kind of is in a lot of different pieces. They're like individual little bits that are not stuck to each other, right? So this is not connected. We use the word disconnected, but not connected is a synonym for disconnected. All right, or something like, 0, 1, union, 3, 5. This looks like one interval over here together with another interval over here. This is disconnected. All right. Here's another maybe slightly more interesting example. How about this? All real numbers except 0. So 0 is omitted from this picture. That's pretty ugly looking. I'm trying to make one of those little open circles right there. You know what I mean? All real numbers except 0. So you could write this as r minus 0. All real numbers except 0. Or if you want to, here's another way of writing the same set. Minus infinity to 0, open interval, union, open interval 0 to infinity. This is all real numbers except 0. This is disconnected because it's sort of in two pieces. Even though you might feel a little weird about this because the two pieces are kind of infinitely close together, but that they lack that point in the middle, which is supposed to be there to connect them if they were connected. So this is disconnected. All right. One more slightly weird example. How about Q? So Q has sort of, I mean, it has points everywhere, but it also is missing points everywhere. Is this connected or disconnected? This one, without knowing the definition, it's hard to say. You should feel kind of like Q is all those points are sort of together, but they're also kind of separated from each other by a lot of missing points. This, according to the definitions, this is disconnected. But you'll have to see the definitions in order to see exactly why. You should believe me when I say Q, according to the definitions we're about to talk about, is disconnected. It shouldn't really be a surprise, although you should feel like it's not exactly obvious if it's going to be connected or not. Okay, let's talk about the definition then. What's difficult about it is the notion is so intuitive that it's hard to say. Everything that I've said so far is not really constitute a definition. I said you can't break it into two separate pieces, but I didn't define what I mean by separate or even pieces, or you know, there's sort of things that are missing that should be there. These are not real definitions. There's actually two separate kind of strategies or approaches, maybe I'll say. Two different approaches to defining connectedness. And one of these that I'm about to describe is written in the book as the definition. The other one is proved as a theorem. The definition is equivalent to this other approach. I'll just tell you the two approaches to begin with. The first one involves individual points and points which are in between other points. So the first approach I'm going to think of like in terms of points and between points. And this one says that some set, so in our book they use the letter E for a connected set. E is connected when, the idea here is you think of one of these, a set, and if I have 2 points that are in the set, A and B, and another point C, which is in between, if it's connected, it means that C is also in the point, is also in the set, right? So one way of thinking about connectedness is whenever you have 2 points in the set, every point in between is also in the set, which means this set on its inside never has a gap in it, or it never has a break in it, because for any 2 points in the set, all of the in-between points are also in the set. So I'm going to say E is connected when if A and B are in E, and C, a real number, is like this, A is between A and B, then C is also in my set. So what this is saying is connected. It means there's no gaps in between any of the points of the set. So if you have 2 points in the set and another number which is in between them, that other number must also be in the set. There are no gaps in between points. All right. This, I think, is a good definition, and it makes sense. But it turns out this is kind of hard to use as a definition. Like all those examples that I just wrote up there, to demonstrate that those sets are connected or not connected using this definition is not very easy. There's another more convenient definition, and it is in terms of breaking the set apart into smaller chunks. So this one is, I'm going to say in terms of, I'll say separating maybe components of the set as a fancier sounding word than chunks. I'm going to try to say something like you cannot break the set up into two separate bits or chunks, right? This, what I'm about to write, is what the book calls the true definition of compactness or connectedness. So I'm going to write this as a real definition here. So in fact, it turns out to be easier from this point of view to say what it means to be disconnected. So here's the definition of disconnected. E is disconnected. Remember, the picture you should have in mind is like this. It's under my face. Like this, right? Disconnected means it has just two separate chunks to it. E is disconnected when we can write E as a union of two chunks, right? The A and the B is the idea. Come on, that's under my face again. My beautiful face is getting in the way. All right? E is disconnected when we can write E as a union of two separate chunks like this. Now, it's not enough to just say A union B, because any set you want to, you can write it, you can just split it into two halves. That doesn't mean it's disconnected. The important thing is that those two halves don't have any overlap and they're sort of far apart from each other. They don't intersect at all. So I'm going to say when we can write E as a union of two halves and they don't intersect at all. Now, I am going to say this. A intersect B is the empty set. That means there is no overlap between those two sets. So you can write the original set in two separate pieces, and those two pieces have no overlaps. Actually, this, what I wrote here, is still not enough because, for example, you could always write something like R as something like minus infinity to 0, union, close interval 0 to infinity. Here I wrote R as two separate pieces, and these pieces have no overlap. The one on the left does not include 0. The one on the right does include 0. They have no intersection, though. But of course, that doesn't count as separating R into two separate chunks, because these two chunks, they meet up right at their edge point. The true definition, and this is something that really, you know, a casual person would not come up with this idea, but I hope you can understand that this is the correct idea. What you need is this. A closure intersect B is empty, and A intersect B closure is empty. All right? So the reason we put those closures in there is to make sure that these two chunks, not only do they have no overlap, but they also don't like just barely touch each other on their boundaries. We're saying A closure. Remember, A closure means all the points of A plus additionally all the limit points of A, which is basically like throwing in also any boundary points. So we're saying A and B, they have no overlaps, they have no points in common, and even if you include the boundary points of A, they do not overlap with any points of B. And similarly here, A intersect B closure has to be empty. That is, A and B, they share no points, and even if I include all the boundary points of B, they still don't share any points of A. All right. This is the definition of disconnected, and then the definition of connected is just the opposite of that. E is connected if it is not disconnected. So using this definition, actually, it's much easier to show something is disconnected than it is to show something is connected. All right. But this is the definition of connected. Now that other thing I said before about points being in between other points, we're going to talk about that but it'll be as a theorem that the connected in this sense about separating into two separate components is the same as that business about points in between other points. All right. I thought we got 4 minutes left. Let's just go through those examples that I said informally before and see if we can demonstrate, at least the disconnected ones, let's see if we can demonstrate that they are indeed disconnected. It's not so hard to do, usually at least. To show something is disconnected, you need to demonstrate what are the two parts that you're going to break it up into. So, for example, I will do the easiest one. We had this as one of our examples up top. 0, 1, union 3, 4, I believe. This is disconnected. How do you demonstrate that? You must describe this in two pieces. You've got to say what are the two pieces. Now this set is here and here, right? I think in this case it's obvious what the two pieces are. The two pieces, I'm going to say let A be 0, 1 and B be the interval 3 to 4. I'm using closed intervals because that's what they are in this set. And then is it true about those intersections? Then let me just say a closure. I'm about to check these two things that they are satisfied, because this is what's necessary in order to be disconnected. In order to check these, let's just say what is A bar and what is B bar. A bar, the closure, is also the closed interval 0 to 1. A is already a closed set. It already contains all of its limit points, and so when I take the closure, I just get the same thing again. And then B bar is also, again, the closed interval 3 to 4. Okay, and it is true, A bar intersect B, what is this? That would be the interval 0 to 1, intersect the interval 3 to 4. And that's the empty set, right? Those two sets of numbers have no overlaps. The interval from 0 to 1 and the interval from 3 to 4 do not intersect. And we also need to check A intersect B bar. But this is still 0 to 1 intersect. B bar is 3 to 4. And again, they have empty intersections as desired. All right? Suppose you could say that's a miniature proof. Very miniature. You don't really have to say much at all. You do have to say what are the two sets that you're going to break this into to make the argument that it's disconnected. All right. Let's see if we can do the other examples. We've only got like 1 minute left. Maybe we'll just do one more and then we'll leave some more for next time. If we had more time, I would make some breakout rooms. Everybody loves the breakout rooms, right? I don't know. How about, this was an example. R minus the origin, or R minus 0. That is everything except the 0 is disconnected. Let's see if we can demonstrate that. You got to tell me what is the A and the B. What are the two halves of this set that you're trying to break it into? They don't have to be exact halves. They're just two pieces that you break the set into. What do you think? I think this one also is kind of obvious. I should take the part on the left, minus infinity to 0, and then B should be the part on the right, 0 to infinity. All right. And then what are the closures? The closure of this means I take the same stuff, but I add in all of the endpoints, which in this case is just the 0. You can't add in the endpoint at infinity because that's not an endpoint. That's not a point. But the closure of this A is minus infinity to 0, the closed interval. And B, the closure of this one, is closed at 0 up to infinity. And then can we verify that those intersections are empty? I need to do A bar intersect B and also A intersect B bar. All right, what is it? A bar intersect B, that would be minus infinity to 0, closed there, intersect 0 to infinity. And that really is open. You might worry, don't they overlap at the point 0? They don't actually intersect at 0 because 0 is only in this one, right? 0 is in this one, but it's not in this one over here. So this is empty. And for the same reason, this one is also empty. This would be minus infinity to 0, open, intersect, closed interval 0 to infinity, and that one is empty too, so it's disconnected. All right, and I think that's all the time for today. Sorry, this was a little heavy. Got a little lighter towards the end. We are going to talk more next time about connectedness. Please let me know if you have questions about the test. I'd be happy to help out. All right, see you all tomorrow.